In this video, I'm planning on going over this problem. This is out of Thermodynamics and Engineering Approach, CBK, the 8th edition. And this problem is most likely in other editions as well, although it'll have a different number. So this is for a turbine, and it says that steam flows steadily through an adiabatic turbine, and it gives us the inlet conditions, or some of the inlet conditions, some of the exit conditions, the mass flow rate, and it wants us to calculate the change in kinetic energy, power output, and the turbine inlet area. So what I'm going to do, this problem already has a drawing, but I always do another drawing anyway, just because I feel like as I draw a diagram of the problem and write down the information, it helps me to kind of understand what I'm solving, what I already know, and what I'm looking for. So I'm going to call this the problem setup, and you want to approach all of your problems like this. Like, you want to go through these steps to set up your problem. So we're going to have a problem setup, then we're going to make assumptions. You need to make assumptions, otherwise a lot of these problems aren't solvable without using quite a bit more complicated math and probably a computer, a numerical solution to solve your problems. So that's why you need to make assumptions. A lot of these equations also have assumptions built into them, so if you're not making a certain assumption, you can't use all of the equations that you might want to use. And so you need to be really clear what your assumptions are, how you're setting up the problem, and then after we do those two things, we're going to go through what equations we're going to use to solve this, and then very last we're going to plug in numbers and calculate the answers. So a lot of people jump right into just trying to write down equations and plug in numbers, and that's not how you want to set up these problems. You might get the right answer sometimes doing it that way, but a lot of times you won't, and you really want to learn how to set up your problems, not just for this class, but for all of your future engineering classes as well. So let's go ahead and start setting this up. So I'm going to draw a turbine, even though there's already a drawing of one. I'm just going to draw one so that I'm pretty clear what's going on. So the turbine has flow in and flow out, and it says that we have steam, and since it's a turbine, there's going to be some work out, and this work is likely rotating a shaft in a generator and producing electrical work, so that there's going to be some work out. So the steam we're basically extracting work from the steam as it condenses. Alright, now let's write down some of our information. So it says the steam flows steadily. The steadily is a huge clue. That means that we can assume that this is steady flow. So this is going to go under our assumptions, but I'll just write it down now since it's right there in the problem. Sometimes your problem won't say that your system is, or whatever it is that you're analyzing, is steady or flows steadily or a steady flow. But whenever you have these problems where you have mass flowing in and mass flowing out, and it's not in a startup or shutdown phase, you pretty much are going to assume that it's steady flow. It wouldn't make sense otherwise. Like, if you think about this turbine, we have steam flowing into the turbine and steam flowing out. Steady flow means that the mass flow rate doesn't change with time. So in other words, your time derivatives are zero. So if we have steam, so if you think about this, okay, let's say that we have this turbine, we just turned it on, and we have steam flowing into the turbine. Well, initially during that startup, your mass inside the turbine is going to be changing with time. So your mass is changing with time inside the turbine. during the startup, and once it's operating steadily, so here's the steadily again, or in steady flow, that means that the mass inside the turbine isn't changing with time, and that just intuitively, you know that means that the mass flow in has to be equal to the mass flow out. So what we can say by the steady flow is that m dot 2 is equal to m dot 1 is equal to m dot. And it actually tells us what the mass flow rate is. So the mass flow rate is 12 kilograms per second. You'll see different terminology for this steady flow. So steady flow, in this problem, they're just saying flows steadily. So you'll see this different terminology. You'll also see steady state. So all of these mean that basically you can assume that the mass inside your system, in this case our system is the turbine, isn't changing with time. So I'm just going to draw the boundary. So this is what we're considering to be our system. Alright, so let's write down some more stuff. It's adiabatic. That means that this turbine is likely well insulated, so there's no heat in or out. So right away we know that Q dot is 0, so there's no heat in or out. And we can also just add this to our assumption. Alright, now it says that, so now it's giving us the inlet conditions. This is our inlet, this is our outlet. So the inlet, it says that the pressure is 4 megapascals. The temperature is 500 degrees Celsius. And it tells us that the velocity of the fluid is 80 meters per second. And then it gives us the exit conditions. So at the exit, the pressure is 30 kilopascals. And then it gives us a quality, 0.92. So since it gives us a quality, that means that we know the outlet, the phase of the outlet is a saturated mixture. So it's a mixture of liquid and vapor. Going in, since it says it's steam, we're gonna look up this pressure and temperature and verify, but this is most likely a superheated vapor flowing in, and then we have a saturated mixture flowing out. And then it tells us the velocity out is 50 meters per second. And then we want to find the change in kinetic energy, so we're looking for the change in kinetic energy and the power output, so this work isn't given, but we want to find it, and the turbine inlet area, so we're looking for the area of the inlet. Alright, so we have our problem set up, and I know that there was a drawing here that has exactly what we wrote down, but I think it's good to just ignore this and rewrite the information, because like I said, as you're writing it down, you're going to get ideas of assumptions you can make and really understand the problem and the problem setup. So we have basically our problem setup. We have the drawing known, we have the knowns and the unknowns, and we have some assumptions. So let's make some more assumptions. One assumption I want to make, so the steady flow and adiabatic are already here, but there's not going to be, it doesn't say anything about this turbine being really tall. So basically we can assume that there's not a large elevation difference between the inlet and the outlet, so we're going to assume that the change in potential energy is 0. Alright, now let's write down some equations. And I want to point out that setting these problems up, writing down your assumptions and the equations you're going to solve, is probably the most important part of these problems. Just plugging in numbers into an equation and possibly getting the right answer or not getting the right answer doesn't mean that you need to know how to set up these problems. And so I would consider this part and the part I'm about to do probably the most important part of these problems. So what you don't want to do is just skip all of this, write down an equation, and try and plug in numbers and see if you get the right answer, because you might get the right answer, but you might not. And if you do get the right answer, you might have just happened to plug numbers into your equation right, but you want to know exactly where your values are coming from, what the assumptions in the equations you're using are, and what exactly is going on in your system, and why you're using the equations you're using. Okay, so let's look at what we have before we write down the equations. So basically we have a turbine. We have what is most likely superheated steam going into the turbine, and we have a saturated mixture coming out. And so there's a large pressure drop. Basically, we're extracting energy from the steam and getting work. We're getting work out that's likely being used to generate electricity. And it doesn't tell us T2. I don't know if we're going to need T2, but I'll just write that down anyway, just so we know that we don't have it. Since we know the pressure and the quality, we have the information we need to look up data on the tables for the outlet. We have the pressure and temperature at the inlet, so we have everything we need to look up data on the tables. And we're looking for the work out, the change in kinetic energy, and the area of the inlet. So right away we know that we're going to need to do an energy balance. And so I'm going to write down the energy balance for single stream steady flow, because that's what this is. So we determined it was steady flow, and it's single stream. We only have one stream in and one stream out. So the first law, or energy balance, for the single stream steady flow is Q minus W is equal to m dot H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. And I like writing down all of the terms, even though we know that some of these terms are zero. And I did derive a general energy balance for a turbine in a previous video, and I think in that energy balance we assumed that the potential energy was zero, and I believe we also assumed that Q, or the heat input or output, was zero. And so theoretically you could just take that equation and write it down, and it wouldn't have the potential energy term or the heat term. But the problem is, what if your turbine, what if you do need to consider the potential energy? I don't think you'll need to for a turbine unless it's giant. But the turbines are often well insulated, but if they're not, then you could potentially have heat into or out of the system. And so anyway, but we know that the change in potential energy is zero. Q is zero in this case, and it's giving us some velocities, so we need to keep our kinetic energy term as well. So then we have the work is equal to m dot H2 minus H1 plus V2 squared minus V1 squared over 2. And then, since this term is the change in kinetic energy, and it's on a per mass basis since we're multiplying it by the mass flow rate here. So this term is the change in kinetic energy, which is one of the things we're looking for. So I'm going to actually just change that term in this equation to the change in kinetic energy, and then we have the negative work is equal to m dot H2 minus H1 plus delta KE. And then I'm just going to write down the equation for delta KE. So this is actually what we're going to be solving. So this is equal to V2 squared minus V1 squared over 2. Normally I would just solve that directly in the energy balance, so I would actually solve this equation, but since it's asking specifically for the change in kinetic energy, I'm just going to calculate it separately and then plug what I calculate into this equation. So basically then I'm not having to solve for that kinetic energy term twice. And then we have, and the other thing we're looking for is the work. We know the mass flow rate because it was given. We can calculate the change in kinetic energy because we were given the velocities. And we need the enthalpies. So we're going to get the enthalpies from the tables. We have all of the information we need to look those up. The last thing that it asked us to calculate was the area of the inlet. So we can calculate that because we know that the mass flow rate, so m dot, is equal to the area multiplied by the velocity divided by the specific volume. And we can look this up on the table. So I'm just going to put table. I think these are all the equations we need. I'm going to solve for the kinetic energy first, and then I'm going to plug that into the energy balance and solve for the work, and then very last I'm going to solve for the area. So now let's look up data, and at this point in this analysis, this would either be looking up data on the tables, getting your, like if you're using specific heats to calculate your change in enthalpy, you would look up your specific heat at this point. So this is really just getting all of the data that you need to solve the problem, just depending on how you're solving it. So at the inlet, the pressure is 4 megapascals and T1 is 500 degrees Celsius, and this is 4,000 kilopascals. So what I want to do first, I mean, I'm fairly positive this is a superheated vapor, but I just want to verify that to make sure that I'm assuming the right phase, because if it's not a superheated vapor, we can't use the superheated vapor table to look up the enthalpy and the specific volume. So we want to determine the phase. So what we're going to do is look up the temperature of saturated liquid at 4,000 kilopascals and compare that to the temperature of our system. So Tsat at 4,000 kilopascals is equal to 250.33 degrees Celsius, and so our temperature is greater than Tsat, so this is in fact a superheated vapor. So then we can use the superheated vapor table to look up our enthalpy and specific volume. So we're going to look up P1 and T1 on the superheated vapor table, and this is for water. So V1 is equal to 0.08644 meters cubed per kilogram, and the enthalpy is equal to 3446.0 kilojoules per kilogram. Alright, so we have our information at the inlet. Now let's look up our information at the outlet. So we already know that this is a saturated mixture because it gave us a quality. If you have a quality, that means that you have a saturated mixture, because a quality doesn't make sense for, say, a compressed liquid or superheated vapor, because your quality is just telling you what percentage of vapor you have. So P2 is equal to 30 kilopascals, and the quality is equal to 0.92. And so we know that our enthalpy is equal to the enthalpy of the saturated liquid plus X multiplied by the enthalpy of vaporization. And remember, this is just the enthalpy of the saturated vapor minus the enthalpy of the liquid. But we can look this up directly, so that's what we're going to do. So the enthalpy of the saturated liquid is equal to 289.27 kilojoules per kilogram, and this is equal to 2335.3 kilojoules per kilogram. So then we can calculate the enthalpy, so H2. And remember, I'm just looking these up on the saturated table for water, and I'm looking at the pressure table because I know the pressure. So the enthalpy at the outlet is equal to 289.27 kilojoules per kilogram plus the quality, which is 0.92, multiplied by 2335.3 kilojoules per kilogram, and this is equal to 2, so H2, the enthalpy at the outlet is equal to 2437.75 kilojoules per kilogram. So this is the data we need for the outlet. So now we should have everything we need to do our calculations. So now last, we're going to do our calculations. All right, so I'm going to calculate the kinetic energy first. So if we go back up and look at the equations we're solving, so first I'm going to calculate the kinetic energy, then I'm going to plug what I get for that into the energy balance and solve the energy balance for the work. And we know the enthalpy at the inlet and outlet because we just looked them up. And then last I'm going to calculate the area from this equation for the mass flow rate. So I'm going to go down here and I'll rewrite these equations so we know what we're solving. So the change in kinetic energy is equal to V2 squared minus V1 squared over 2. And this is equal to 50 squared meters squared seconds squared minus 80 squared meters squared seconds squared over 2. And so this is where it can get a little bit confusing. We have units here of kilojoules per kilogram, but it looks like over here we have units of meters squared seconds squared. So we need to use this conversion that 1 kilojoule per kilogram is equal to 1,000 meters squared seconds squared. So we're going to put this conversion in so we can get the kilojoules per kilogram. So we have 1 kilojoule per kilogram over 1,000 meters squared seconds squared. The meter squared second squared cancels and we're left with kilojoules per kilogram, which are the units we want. So the change in kinetic energy is equal to negative 1.95 kilojoules per kilogram. So that's our change in kinetic energy. Now we want to solve our energy balance. So that was this equation. So I'm going to go back down here. So, and make sure you keep your signs for the work and the heat. We cancel out the heat, but don't change any signs at this point. And then this is plus the change in kinetic energy, which we just calculated. All right. So now I'm going to multiply this by a -1 just so that I can get the work. And then I'm going to have negative m and then still H2 minus H1 plus the change in kinetic energy. Now we can just plug in all of our numbers. So we have the work is equal to 12 kilograms per second multiplied by, and then we have the enthalpies that we looked up. So this enthalpy at the outlet is 2437.75 kilojoules per kilogram, minus the enthalpy at the inlet was 3446.0 kilojoules per kilogram, and then we have plus our kinetic energy, which we calculated here. So this is going to be negative 1.95 kilojoules per kilogram. Now let's just make sure our units work out. So we have kilogram here, that's going to cancel out all of these kilograms, and we're left with kilojoules per second, which is what we want because we're looking for the so this work is, this dot means that this is on a per time, so this is, the units for this are like kilojoules per second or kilowatt. So this is a unit of power. But basically, we want kilojoules per second, so that means that our units look correct. So this is going to work out to, the work is equal to 12,122 kilowatts, and then we can convert that into 12.1 megawatt. And the work is positive because the work is being done by the system. Alright, now last we want to calculate the area of the inlet. So we know that m dot is equal to the area multiplied by the velocity over the specific volume. And just keep track of these. They're both represented by V's, so it might get a little bit confusing, but this is specific volume. The cursive V is velocity. Alright, so what I'm going to do is solve this equation for the area, and then I have everything I need. I know the mass flow rate, I know the velocity, and I know the specific volume at the inlet because I looked it up. So if I solve this for the area, all I need to do is plug in values. So the area is equal to m dot multiplied by the specific volume over the velocity. So this is equal to 12 kilograms per second multiplied by 0.08644 meters cubed per kilogram. And remember, this is what we looked up. And then we have 80 meters per second for the inlet velocity. Let's make sure our units work out. So the kilograms cancel, seconds cancel, and this cancels, and we're left with meters squared, which is what we want for an area. So this works out to 0.013 meters squared.